మెయిల్లో ఉంది, అది కొంచెం మోడిఫై చేశాను.
Check. Sino sir, good afternoon, sir.
Hello, good afternoon.
Sir, thank you. Thanks a lot, sir. Thanks for joining, sir. So Professor Vipul was talking, he will be late by 10 minutes, sir. So he asked us to start proceedings and he will join, sir.
Yeah, you can start.
Okay, sir. So as I mentioned in the email, it is a pre-talk and synopsis of my student, Mr. Risteja, and he is working on feeding terahertz integrated circuits with SSPP. You are also there in the comprehensive examination, sir. So now he is about to submit his thesis. So now I am giving it to Mr. Risteja, and he will start the proceedings. Thank you, sir. So,
Good afternoon to all the respectable DC members who joined online for my.
సార్ చూడాలంటే
Good afternoon to all the respectable DC members who has joined online for my pre-talk and synopsis presentation evaluation on the topic of smooth surface plasma and polariton. And very good afternoon to all the faculties and my dear colleagues who has joined here with me. Now I'm going to give a pre-talk and synopsis presentation of my topic smooth surface plasma and polariton. In the last presentation, I mean in the comprehensive Viva presentation, the respectable DC members have raised some queries, which I was, and those are minor queries only, not major queries. And I believe that my presentation satisfied them a lot, and I believe to my knowledge, and they have raised some few questions, which I was unanswered at that time. And I hope in this presentation, I will acknowledge that to the best of my knowledge. So now let me just start my presentation. The thesis topic of my presentation is feeding terahertz integrated circuits using spook surface plasma and polariton. So before going to talk about my thesis topic, we have to concentrate on the term spook surface plasma and polariton. So basically, polariton is a propagating wave. If it couples with surface, if it is the coupling of surface plasmon and electromagnetic wave results surface plasmon polariton. Similarly, if we have coupling of phonon and electromagnetic wave, we'll get phonon polaritons and so on. So why these are very useful? It is very useful because let us think of a waveguide. For example, let us consider a wire which carries electrical signal, and next let us consider an waveguide that carries optical signal. By using spook surface plasma and polariton, we can design a waveguide that carries plasmons. So it is it is very useful in on-chip communication. So it is one of the potential ways by which we can combine electric signal as well as optical signals through it. And it has receiving a lot of attention in the last 2 decades. With this introduction, I can start my presentation, and I'm working under the research supervisor of Dr. Srinivasulu Tupakula sir, EC department. Sorry, the slides are not. So here are my course registration details. So my registration number is that, and my date of joining PhD is 2019 November, and my first DC meeting was conducted in 21, and my comprehensive viva held in June 24, and these are my exam mark details, I mean coursework subjects, and I have cleared all of them with CGPA of 8.25. And coming to my contents, here we go with introduction, followed by research issues and solution approach for that, and followed by literature review and problem statement, what I'm actually going to work on, what I'm actually going to state. That's my problem statement in my research. And next objectives, what I have tried in my research, and next methodology and research design, how I done that, and outcomes. So what are the results I obtained so far, and next list of publications. So here is the short review. So let us discuss about this RF through terahertz portion of the electromagnetic spectrum. So when I am saying here terahertz portion, I'm specifically emphasizing RF through, if I'm this slide talk about the RF through terahertz spectrum, terahertz portion of the electromagnetic spectrum. So when I say terahertz portion, I'm specifically emphasizing that. And here, so RF frequency range starts from 9 kilohertz to 300 gigahertz. And here, there is no predefined specification for the terahertz region here. Some of them may consider 0.1 terahertz to 10 terahertz, and some may be considered at 0.3 terahertz to 30 terahertz, and some may take it as 300 gigahertz to 30 terahertz like that. But there is general consensus on the researchers that 0.1 terahertz to 10 terahertz will be the exact terahertz portion that has been found in the literature. So now here there are several millimeter frequency bands that has been opened in different countries, and in India also we are trying in the range of 26 to 27 gigahertz. We are working on it. These are called as sub-millimeter terahertz frequency ranges. So here the drawback is that the researchers here system cost reduction is very major obligation here. We need to work on that. Bringing down the system cost is one of the major challenge for the RF engineers and RF designers who is working in sub-millimeter terahertz band, and we are working on that. And FCC communication standards has allocated frequency bands for mobile, satellite, and wireless communication links around 300 gigahertz, but the bands has not been allocated so far for communication applications, and it is anticipating that in the future R&D applications will emerge and the spectrum requirements will be updated, and then the frequency bands will get allocated. So here, coming to the motivation, there have been relatively smaller studies, I mean very less studies in the data transmission using terahertz communication till date. Why? Because there is no possible compact components that are available in the communication systems like planar integrated circuits, amplifiers, and antenna arrays doesn't work above 140 gigahertz. So here there are two possible potential candidates here for terahertz research. 140 gigahertz is one of the possible potential candidate, and 330 gigahertz is another possible potential candidate here we are working on. So here the problem is that the required compact components for communication systems like planar integrated circuits and other antenna arrays doesn't exist above 140 gigahertz. So that is the major drawback here. And in this regime, vast research scope exists for the researchers to develop compact integrated circuits in terahertz range. So this is my motivation step to lead this research, and I am exploring this. And in my couple of slides and in the next slide itself, I will discuss my research issues. So in this vast research scope, what are the complications that we are going through to develop compact integrated circuits? That's I'm going to discuss in the next slide. That is the research issue. Next generation radio frequency communication and sensor systems requires miniaturized and reconfigurable components that requires which reduces the power consumption, cost, size, and weight. That is our primary objective here. So if you take the copper interconnects, they suffer with major limitations like signal and clock distortions, attenuation, impedance matching, crosstalk, and several other problems. So if you go to the lower frequency range, the situation will be very worse in the communication. So signal can't propagate. There will be a lot of losses will be occurred for copper interconnects if you use copper interconnects in the transmission lines. So alternate solution is we are designing the waveguides. But however, these waveguides will also suffer from cutoff conditions. So that is the major drawback here. So if we rectify though the waveguides will rectify the issues of copper interconnects like attenuation, clock distortion, impedance matching, everything, but still it suffers with cutoff conditions that we need to focus on here. So here, these are the well popular guiding structures that we have come across in our guiding waveguide technology, like microstrip lines, suspended microstrip lines, coplanar waveguides. So here the thing is that it can be used for only lower frequency guiding purpose. If we use it for higher frequencies like terahertz and higher frequency range, beyond that it fails. So that is the major drawback of this type of conventional waveguides of this. That means if the metallic ground is insulated on the dielectric substrate, that is insulated on the topmost layer of the silicon wafer, then the losses are predominant here. The losses will couples with that of the ground material and circumvents the poor microwave characteristics. So that is the one of the drawback here which we are facing for the conventional type of devices which I am listing here. This can be overcome with surface waveguides. So this can be overcome with surface waveguides. So this is the new design of millimeter wave guiding structure. So here it is a non-radiative dielectric material. Here we have introduced the dielectric material here. So here we have designed the waveguide in below cutoff region. That is the advancement here. So previous designs, we didn't design it for below cutoff region. That's why the size is very high. So here we have reduced the waveguide to its below cutoff condition. So we are taking one below cutoff designed waveguide and we are removing the top and bottom layers and we are setting it as a below cutoff waveguide. And there we have introduced one dielectric slab on that. So the dielectric slab propagates the electromagnetic wave through it. And however, it still suffers the dimensions. So if you try to reduce the A, here if you try to reduce the A, then small a, that means the dimension to the below cutoff level, it fails. The electromagnetic wave won't guide through it. So that is the one of the biggest drawback of this type of millimeter wave guiding system. So the problem is that, is there any alternative to launch the electromagnetic wave that that supports the wave that is propagating through it if you still reduce the dimension to below cutoff region? That is the problem here, and that can be done with the help of plasmonics. So if I have gone through the literatures and there is only one solution I come across, that is the plasmonics. So here, what is the difference between normal waveguide and plasmonic waveguide is that normal waveguides like optical fibers and dielectric materials, dielectric waveguides, if you still reduce the core dimensions to a below cutoff region, then what will happen? The confinement of the wave energy is very high in that, and the wave energy spreads out. So that is the drawback in which we can see in optical fibers and millimeter wave guiding devices. But coming to the plasmonics, if you still reduce the dimensions to a below cutoff region, but still the wave is confined into it. So there is a significant amount of energy that is passing through it without loss of energy that is spreading out. So that can be minimized with the help of plasmonics designs, and that can be done with the help of cylindrical metallic nanowires, gold nanowires, silver nanowires, etc. So this is the best feature of plasmonics. So far I have analyzed, and my step of research is into this. And here most of the RF engineers and RF engineers and microwave researchers are trying to, but actually the thing is that these plasmonics will operate at optical frequency range. So most of the RF engineers and researchers are trying to bring that characteristics of surface plasma and polariton that is passing into the optical range down to the microwave or lower frequency range. So that's why they are doing research on that, and the metals commonly employed in the visible part of the spectrum of surface plasma and polaritons that is propagating at the optical frequency range will, such as gold and silver, have significantly different properties than that of RF through terahertz regime. So if you take that metal and gold nanowires that is operating at the optical frequency range, if you down to that RF through terahertz regime, if you function that, if you try to operate that in the lower frequency range, then automatically there will be some significant, it exhibits significantly different properties. And far below their plasma frequency, these materials will have significantly negative real and positive imaginary parts. So that is the drawback here. And so as a result, the metal behaves as perfect electric conductor in these frequency regimes, low frequency regimes like RF through terahertz regimes. So that's why my intention is to, and it exhibits poor confinement. So this is the problem which we can generally define here. So what is the alternative solution approach for that? The alternative solution approach for that is designing spoof surface plasma and polariton. So spoof means we are just mimicking, we are just copying, we are just reproducing the characteristics of surface plasma and polaritons that is take place at optical frequency range down to lower frequency range, like some gigahertz range or some microwave range, etc. So that can be done with the help of two ways here. First one is lack of confinement of surface plasma and polaritons in the lower frequency range can be overcome with the help of placing semiconductors in place of metals. So in place of metals, we are placing the semiconductors, and we can reproduce the characteristics to the lower frequency range. Or there is one other alternative, that is spoof surface plasma and polariton. Spoof surface plasma and polaritons are the artificially designed engineering structures that produces the same equivalent characteristics of surface plasma and polaritons down to the lower frequency range. So here the metallic surface, top metallic surface has been textured in such a way that the electromagnetic wave can be effectively penetrate into the throughout the waveguide surface. So here by changing the geometrical properties of the, by changing the geometrical parameters of the metallic waveguide, we can bring the functionality to the lower frequency range. So that is the beauty of this spoof surface plasma and polariton. So plasmonics is nothing but is the branch of physics which deals with the optical signals and the confinement and guiding of light at nanometallic structures. So my intention is to design nanometallic structure, and that can, plasmon is nothing but it is the coupling of free electrons. It is the free electrons present in the metallic surface. So that can be divided into two types: bulk plasmons and surface plasmons. And bulk plasmons is bulk plasmons origins with the help of longitudinal wave that propagates along the entire cross-sectional area of the metal. And that I will not talk much about this bulk plasmons right now. My intention is to surface plasmons. My research is that. So surface plasmons is nothing but the electric field. The electric field is perpendicular to the direction of propagation, which is nothing but transverse waves. So transverse waves will dealing with surface plasmons, and that is of two types: localized surface plasmons and surface plasmon polaritons. So localized surface plasmon is nothing but a confinement of the free electrons in the metal. That is nothing but localized surface plasmons, and the surface plasmon polariton means a spoofing concept. So surface plasmon polariton is nothing but it will be available at the high frequency range, and the spoof surface plasmon polariton is nothing but we are bringing down that characteristics to the lower frequency range. So that is my research. And why plasmonic? So why we are interesting into it? So here it gives us scope to generate super fast computer chips and ultra sensitive molecular detectors, and it is the next generation on chip scale technology. I mean, it is the potentially one of the ways in which we can integrate electric signal with that of optical signal. So data can be transmitted as fast as compared to optical fibers and dielectric waveguides. By using this plasmonic waveguide, by designing this plasmonic waveguide, the data can be travels very faster compared to optical fibers and advanced waveguide technologies. So these are the couple of advantages we can specify here. And surface plasmon polaritons. So surface plasmon polaritons, in short, I can say it is the charge oscillations. It is the charge oscillations on the interface between metal and dielectric. Okay, so here if you look at the diagram there, gold film is there. That is one medium, and the air on top. On the top surface, it is filled with air. So there it forms the interface. So along the interface, the charge oscillations will encounter. Charge oscillation will encounter. So that is nothing but surface plasmon polaritons. Movement of that supports the movement of wave forward. So here the movement will be of the wave decays exponentially while it is moving towards the one axis, and in another axis the wave intensity gets exponentially decays on the another axis. So that gives us the high confinement of the electromagnetic wave or plane wave on the interface. So that's what the diagrams is all about. And here, if you want to analyze a brief into it, so let me just mark on the interface, the wave is propagating towards the x-axis. So towards the x-axis, the wave is propagating here, and the intensity of the wave gradually decays exponentially on the another axis, z-axis. So the confinement will be very high. So here on the x-axis, the wave is propagating. So that can be represented with the help of magnetic field here. And I'm just stating here, surface plasmon polariton supports magnetic TM waves, transverse magnetic fields. And here, that's why I have taken magnetic field here, H1y and H2y. H1y is the magnetic field present in the first medium, and H2y is the magnetic field present in the second medium. And that is defined as e to the power of ikx into x. It is the plane wave that is propagating along this x-axis, followed by decay, exponential decay, that is e to the power of minus k1z into z. And here similarly, the same as the tangential component of the magnetic field is conserved in the another medium. So we are representing with the same equations. And here also e to the power of k2z into z. So e to the power of k2z in this sense, here minus is there. So minus of minus, because this is the metal. So that's why metal is the negative permittivity and dielectric is the positive permittivity. So that's why minus into minus, it will get positive here. And we can represent like this. And this is the some mathematical analysis, what is happening on the interface, how the wave is propagating. So that is just a mathematical analysis here. Basically, the excitation of the surface plasmons, polaritons on the interface will be of two types here, TM wave excitation and TE wave excitation. So I already stated that surface plasmon polaritons supports TM wave propagation. So that's why TM wave means the magnetic field is along the y direction. So that is known as TM wave. And what is TE wave? TE wave is nothing but the magnet electric field is along the y direction. So that is TE wave. So here let us consider an wave is instant on the interface. Interface between the two dielectric interface between the two mediums in the negative z direction here. So the wave is instanting here negatively along z axis. To show plasmon polarity can exist there, first of all, we have to consider the same equations here, which I have discussed in the previous slide, H1y and H2y. And now here, sorry, I have to start from here. So wave is incident in the negative z direction, right? So here wave is incidenting on the negative z direction. So here, for the first medium, the wave vector we have to consider here as KD, dielectric wave vector, and in the second medium, the the wave vector for the metal is Km. And in the first medium, there are two, it is a xz plane, and y is out of plane, we can't bother about that. So here z and x are the plane surface that is supporting this wave incident on it. So that's why KD is equal to x component is present, kx, and there is no y component because it is out of plane. So 0, and here wave is incidenting on the negative z axis here. So that's why I have mentioned it as minus k1z. And it is holds true for the metal also, as it is conserved on both sides. So now from dispersion relation, we can write this as the terms can be, it is nothing but the sum of these terms that are present on this propagation vector can be equal to free space wave vector terms, that is omega by c whole square. That is the free space wave vector k0. K0 is defined as the free space wave vector. So whatever the terms we got in this, that can be equal to the sum of the terms, sum of the square of the terms can be equal to free space wave vector terms k0 square. K0 is nothing but omega by c whole square, and some refractive index is also present on this material, and that is represented with n square. So here n is nothing but root of mu r into epsilon r. This is non-magnetic medium, so that's why mu r is equal to 1. So then you will get epsilon m into k0 square. Now if you simplify this k2z, it will come like this. If you take this kx square to that side, it will come like this. And finally k2z square equal to epsilon m into k0 square minus kx square. Here a slight comparison we need to do here. What is kx? Kx is nothing but this x component. X component is nothing but on the interface the wave is propagating. On the interface the wave is propagating here. And what is this epsilon m? I already told you here on it is representing that epsilon is less than 0. That means it is a negative. What happens if the range of frequencies where metal has a negative permittivity? If you substitute that negative permittivity here, epsilon equal to minus. So minus of k0 square plus kx square. Kx is positive always because the wave is propagating along the x-axis, positive x-axis. Then this term will becomes imaginary. So I already so the metallic medium is a complex imaginary term. The refractive indexes are very complicated in that metallic surface. So that's why finally you will get this k2z square as negative. So that indicates k2z is imaginary. The propagation wave vector on the metallic surface, metallic medium is imaginary. So what is its imaginary? Imaginary means there will be attenuation wave or evanescent wave that exists on this metallic surface. So from this we can conclude that light cannot propagate on the second medium. So most of the light gets reflected back to its same medium. Because of the presence of attenuation or evanescent wave on the second medium, most of the light will get reflects back into the same medium. So from this H1y into H2y, finally this can be changed the notation, and I have maintained like this. So here epsilon d equal to 1 and epsilon m equal to -1. So if I substitute here, then I got k2z is smaller and k2z is greater for metal. So this k2z will be smaller for dielectric and greater the metal. I already told you evanescent wave or attenuation wave is present on this, exist on this interface, and that we got here smaller for dielectric and greater for metal. That means if you look at the diagram, the evanescent wave is decaying faster in the dielectric side compared to the metallic side. Metallic side, the decay rate is very small. Metallic side, the decay is very greater. So that's why we are getting very small decay, and here the decay rate is slower. That's why we are getting larger decay here. So that's what we have proved here. Wave decay is faster in the metal. That's what we have proved from this analysis. Next, in order to understand that, we are going here SPP analysis. Everything comes out here with Maxwell equations. That is del cross H is equal to J plus dou D by dou T. So here we are not using any sources or currents here. So J equal to 0. So as no sources of currents are there, so that's why J equal to 0. Now we left with del cross H is equal to dou D by dou T. So here dou D by dou T, D is nothing but epsilon into E, and here we are taking monochromatic plane wave. So monochromatic plane wave means it is exponentially decaying e to the power of minus I omega T. If you differentiate that, you will get minus I omega and minus I omega into epsilon into E. And before slide, this is the expression we find out. And if you take del on both, curl on both sides, if you take del cross H, then it will be represented like this: XYZ, dou by dou X, dou by dou Y, dou by dou Z, 0. And we are taking magnetic field, right? Magnetic field HY and 0, that is equal to on right hand side minus I omega and epsilon into E. So finally, if you cross product this, you will get like this: minus I omega epsilon into E. And finally, here dou HY by dou Z means you have to apply derivative for this function. So e to the power of minus k1z into z, that will become k1z into h1y is represented with h1y into x cap, plus next dou hy by dou x means you have to represent here, you have to apply derivative for this term, then that is nothing but e to the power of x derivative is ikx. So ikx into again h1y into z cap, that is equal to minus I omega into epsilon d into E1. So multiply with both sides with I, simple calculation, you will end up with here, and finally you will end up with this E1 and E2 expressions. Here I request you to note here important feature. Here we started with electric field analysis on the y direction. On the y direction we started with electric field, but at last we got we started with magnetic field on the y direction, but at last we come with electric fields on x and z directions. Right, so this is the best feature that supports TE mode, TE waves, SPP analysis of SPP supports TE wave analysis. So this, from this we can conclude that because we started with the magnetic field on the y direction, and in the results we got electric field E1 and E2 on x and z axis. So from this we can conclude that SPP supports TM modes. So this can be written as HY, EX and EZ. So HY, EX and EZ is nothing but TM wave, and after that HY place EY. EY is nothing but a plane perpendicular to the propagation EY, HX and HZ. It is just reciprocal of this, that is TE wave. So from these two analysis we can conclude this. From this analysis we can conclude this TM wave supports SPP propagation compared to TE wave. And here H1y, and then you will apply the boundary conditions here. Magnetic field, the tangential component of the magnetic field is continuous across the interface. So that's why H1y z equal to 0 is equal to H2y z equal to 0. Finally, you will get H1 is equal to H2. Next, you have to apply the tangential electric field for parallel component also. So parallel electric field is also tangential. It has to be conserved on both the mediums. So that's why if you apply this, you will get here omega common terms, you can neglect this, and finally you won't bother about this z because it is out of plane here, because it is normal component, so we can't bother about it. I am just applying here tangential component here. So finally I will get finally I will get these two are equal, h1 equal to h2, then I can remove this. So k1z by epsilon d is equal to minus of k2z by epsilon m. So from this comparison, I will end up this relationship. So this is the most important significant relationship for the surface plasmon wave that exists on the interface. So here k1z by epsilon d equal to minus k2z by epsilon m. So finally k1z by k2z equal to minus epsilon d by epsilon m. So here k1z, k2z are propagation wave vectors on the dielectric medium as well as metallic medium. And epsilon d and epsilon m are the permittivities that present on the interface of both dielectric and metallic mediums. So here I got negative sign, right? Negative of permittivity. So left hand side I didn't get any negative term. That means that it is not positive. It is also negative. So in the next slide it is clearly mentioning here. See here metallic, for the metallic medium. I already told you metallic medium is a complex imaginary medium. So there the permittivity is negative, right? Their permittivity is negative. From that we can clearly estimate that K2Z is negative. K2Z is nothing but metallic medium. So that's why I have to mention here negative, and here I have to mention it with positive. So these terms are nothing but this term only. This equation only I have modified this, and final square root of n1 into k. K square is nothing but free space propagation omega by c and 1. So now from this, if you simplify this further, k1z by epsilon d, if you take this to left hand side, plus k2z into epsilon m equal to 0. So finally we'll ended up here. So from this analysis, we can justify that k1z and k2z are of opposite sides. So on the right hand side also, any one of the medium is of negative, and that is of metallic medium. By default, that is of metallic medium. Then only the wave, the electrons oscillates, couples with that of electromagnetic waves, polarized charges on the dielectric material, and the wave propagates further. So that is the justification here I am giving to exist the surface plasmon polariton waves, and here mathematical analysis of dispersion equation. So coming to TE mode, that doesn't support the surface plasmon polariton modes. I'm stating this from beginning itself. Coming to the TM mode, this is the vector Helmholtz equation, and from this, these are the possible solutions Ey and Hy. And if you apply this for dielectric interface, Z equal to 0, Z is greater than 0, and Z is less than 0. Z is less than 0 is negative, Z is greater than 0 is dielectric, that is positive, and Z equal to 0 is interface. So for Z greater than 0, these equations will reduce like this, Hy and Ey and Hy and Ey. So now, by applying the boundary conditions for TM waves, first boundary condition is tangential component of magnetic field, because I'm taking here TM analysis, not TE analysis. Only TM analysis. So Hy boundary is continuous. So Z equal to 0, Z equal to 0, metal and dielectric is also continuous. And the second boundary condition is dou Hy dou Z. The variation of the wave is also continuous. So that is the second boundary condition. If you apply these two boundary conditions to these equations, 1, 2, 3, 4, first you apply Hy equations. On Z greater than 0 and Z less than 0, apply Hy equations. Apply the first boundary condition, Z equal to 0, Z equal to 0. So here Z equal to 0 means Hy equal to B, and here also Hy equal to D. Finally, you will get D is equal to D here, because e to the power of 0 is 1. And if you apply the second boundary condition, you will get this expression. Minus root of beta square minus k naught square into epsilon s by epsilon s equals square root of beta square minus k naught square epsilon m by epsilon m. So here, from this, if you still further simplify this, finally you will end up with surface plasmon wave vector dispersion equation. This is very important analysis which led the research forward. So this is the important relationship here, omega by c root of epsilon s into epsilon m by epsilon s plus epsilon m. And one of the respectable DC member, Professor Srinivas sir, has instructed me to solve this equation further. I mean, as metal is the complex refractive index exists on the metal, so try to enhance this equation. He suggested me in my CV presentation, and as there are, I have checked all the literature and all the textbooks and all the things, but I find only this expression in all the literatures. In all the literatures and all the webinars and all the video lectures, this is the expression of surface plasmon polariton wave vector. I have to refer the standard textbooks and standard authors so that I can get a more knowledge on that, because as of now, standard textbooks are not available in my work location. Soon I will address this within a couple of, within 10 days or 20 days, I will address this issue, sir, and I will get back to you. So next, non-existence.
Yes. Okay, you are doing that. Fine. Please go ahead.
Sir, I'm doing, sir.
I'm just looking whether TE you have or not. Okay.
May I interrupt?
Yeah, please. Okay.
Yeah, I think if I am not wrong, this is pre-synopsis presentation.
Yes,
Is
sir.
it correct?
Yes,
So I was expecting that here you will discuss the research problem rather than these basics. These are very basic things, no, about surface plasmons. So I don't know why we are spending time on these basics.
Okay,
These
sir.
of course you need to know. All right, but you need not to present all these things here. These are very basic things. I was expecting that you will discuss research problems here.
Yes, sir. I will skip this, sir. I will go to that, sir.
Yeah, please.
Thank you, sir. Thank you very much. So why do we care about SPPs? So this is the wide most important advantages which we are projecting here, because surface plasmon polaritons are highly subwavelength, and we can design subwavelength miniaturized structures here by using surface plasmon polariton concept. We can miniaturize, we can reduce the size of the structure, and we will define nanometer scale dimensional waveguides, and that supports plasmonic integration with other photonic devices. Also, we can directly integrate that devices, and it offers strong dispersive properties. And this is the new mechanism. And the applications are sensors, data storages, light sources, microscopy. We can apply this in everything. And limitations is that SPPs do not found in the lower frequency range. That is the major limitation here. So it is found in only infrared and optical frequency and slight above frequencies only. It doesn't obtain at the microwave frequency range. That is the major limitation here, because in the microwave frequency range, metal behaves as perfect electric conductor. So that is the major drawback here. And the alternate approach is that designing spoof surface plasmon polariton. Spoof surface plasmon. Spoof means copying. We are just mimicking. We are just copying the characteristics of the original surface plasmon polaritons into the lower frequency range. That is nothing but spoof surface plasmon polaritons here, and whose surface has been textured so that the electric field effectively penetrates now compared to the effectively penetrates now in spoof surface plasmon polaritons. The geometrical parameters of the surface structures has been changed. Changing the geometrical parameters of the surface structures, we can design these spoof surface plasmon polaritons, and these are the artificially engineered surface structures here. This is my research. And advantages of spoof surface plasmon polaritons. What are the advantages? It offers strong field confinements. If you still reduce the size of the core to a below cutoff region, the wave doesn't escape outside. So that is the first and foremost advantage here. It offers strong field confinements, and it is used for feeding high frequency terahertz devices. Spoof surface plasmon polaritons acts as a feeder source to feed the high frequency devices, such as that is operating in millimeter waveband and more than that. So that is the one of the advantage here. And if you compare it with microstrip level of feeding, it fails, because there we will increased losses will be there for high frequency. Can't apply microstrip feeding to the high frequency devices. So that is the one of the peculiar advantage here I'm mentioning. And the third one is SSPP feeding can be easily integrated with plasmonics and other nanoscale devices, and it is not with the microstrip feeding techniques. So microstrip feeding techniques we can't integrate like that. So that is one of the advantage here. And one more thing, it offers wide operational bandwidths. So that is also one of the important advantage. And we can design compact layouts, and the ease of fabrication is very easy, and low fabrication cost. Everything are advantages. And coming to the literature review, this and all I have discussed in my CV curriculum, my comprehensive Viva presentation. Because to know some others who are new to this, I'm just recapping this literature review. Surface plasmon polaritons applications are super resolution imaging, on-chip integrated circuits, biophotonics, microscopies, etc. Now the problem is that those surface plasmon polaritons I have to bring to the lower frequency range, and I have to design the compact integrated circuit. That is my research problem here. And that has been laid stone by the scientist J.B. Pendry in the year 2004. He proved that spoof surface plasmon polaritons exist at the lower frequency bands. The characteristics of the surface plasmon polaritons exist at the lower frequency bands, and he proved that by designing corrugated metallic surfaces and perforated metallic surfaces, and he obtained this type of dispersion diagram. And this is the primary dispersion diagram here. The primary dispersion diagram according to J.B. Pendry is that omega by C 1 plus d by p whole square tan square omega h by c. So here d, p, h are nothing but the dimensions of these corrugated metallic surfaces. So p, h, d are the dimensions of the structured surfaces. So now if you make this as 0, then you will get a propagation constant as omega by c. So there is no change in the wave doesn't bind to the surface if you have only omega by c here. So and the waveguide corresponds to a planar surface. So resulting in omega by c. Now if this dp omega, if this dp omega are not equal to 0, then there exists spook surface plasma and polaritons exist, and the strong confinement along the surface will encounter. So how to choose? Now the question is that how to choose these dimensions? That is the bigger question here. So that can be overcome by this, that can be stated by this scientist J.B. Pendry in his expressions. The wave number becomes infinite when pi by 2. And from this, if you want to calculate the maximum frequency, take these terms to that side, then you will get pi c by 2h. And finally, you will get maximum frequency as c by 4h. This is the asymptotic frequency limit. So we have to choose the dimensions. We have to choose these dimensions below this asymptotic frequency limit only. Then only the wave strongly binds to the surface. Here, the graph strongly binds to the surface. So we have to choose these dimensions in the range of asymptotic limit only or below this asymptotic limit. Here I have mentioned here the dimensions of the designed SSPP unit cells have been decided in such a way that the dispersion curve is below that asymptotic limit. So that means in the millimeter range, nanometer range, micrometer range, we have to choose these dimensions. So we don't extend the dimensions. If you extend the dimensions, it fails. The SPP waves doesn't bond to the surface. So one of the respectable DC member, Dr. Amarjit sir, has asked me in my last CV presentation about this query, and I hope that I have answered this. At that time, I was not answered this. So now I answered this query. So next, decay rate of electromagnetic wave. Next, these are all the couple of existed spook surface plasmon polariton structures. So here, if you compare with microstrip line and microstrip line, this is the microstrip line feeding, and this is the microstrip transmission line, and this is the spook surface plasmon polariton transmission line. What is the difference you observed here is spook surface plasmon polariton transmission line, the confinement is very more compared to microstrip level transmission line. So this is the advancement here for the SSPP based structures. And if the confinement is more, obviously there is a less coupling and crosstalk. So that is mentioning here. So mutual coupling and crosstalk can be automatically reduces if the confinement is more. And these are all the different types of structures in which you can find in literatures. So this is known as dominoes arrays, metallic box shaped elements protruding out of a metallic surfaces. And these are all the couple of structures which we can find in literatures. And this is also ultra thin film, flexible ultra thin film dielectric film type of waveguide design. So it is also found in literatures, and this is also found in literatures. And this, so far we have understand that how this spook surface plasmon polariton has been designed and what are the implications of that. But if you want to know the exact development of the waveguide and to characterize its functionality, everything starts with unit cell. So you have to design unit cell first, and these dimensions has to be lies in the asymptotic level, frequency asymptotic level. They have designed these dimensions. So these are the different types of unit cells existed in the literature. So they have designed all these dimensions in the millimeter range, micrometer range, and nanometer range. So below that frequency limit only, they have designed these unit cells. And if you change any unit cell, then the entire waveguide structure will get changes. And these are the design specifications, substrate information, simulator tools used, and design specifications. What is the dielectric material we have considered, what is the dielectric constant, and everything details here. And the unit cell designs. Here they have designed millimeter dimensions. Here you have designed H and W, D, P, all are in millimeter wave dimensions, because we have to satisfy that asymptotic frequency level condition, and we have to design these unit cells. And these are the dispersions. So if you design like that, you will get the bounded surface plasmon polariton waves. More confinement is possible. So that's what this graph is all about. This is the dispersion graph for different types of unit cells. You will get different types of frequency ranges, lower frequency ranges. And this is also I have discussed. This is nothing but the mutual coupling, mode conversion and matching section. If you want to compare this with the light line or cone frequency, we have to match its momentum. Right from the dispersion to light line, we have to match it by taking the gradually incrementing these corrugated surfaces, right from H1, H2, H3, H4, H5. We have to take as 0.5, 1.5 to up to 4 mm. We have to gradually increase it, then it will automatically matches with this free space momentum, curve momentum. And this is my problem statement. I am very clear with my problem statement that at lower frequencies, it is very difficult to design plasmonic integrated circuits. So that's why we are mimicking the surface plasmon polaritons in the lower frequency range known as Hooke's surface plasmon polaritons. And it offers potential solution of designing plasmonic integrated circuits and compact devices. So that is my problem statement. And these are all the existed designs. These are all the existed designs here, and these are the simulated results of that. And coming to my objectives, I have designed here Hooke's surface plasmon polariton waveguide and analyzed its performance through modified groove width. So this is my first objective. I have designed one SSPP waveguide and analyzed its performance. And second one, I have designed SSPP waveguide. I have designed the same SSPP waveguide. By using this SSPP waveguide, it acts as the feeder for high frequency dielectric rod antenna. I used that SSPP waveguide to feed the high frequency dielectric rod antenna, which is operating in millimeter waveband. And I have successfully evaluated its performance, and I have successfully bring down its functionality into lower frequency range. So that is my achievement here. And these are the methodologies. CST microwave studio I have used here, and the data collection methods I have used with experimental measurement, simulation, and theoretical analysis. And my objective 1 is SSPP waveguide design and analyze its S parameters, and objective 2 is feeder element design and dielectric rod antenna and modified it with a feeder device. So this is my first objective. So here I have designed the unit cell first. So this is my unit cell. For this unit cell, I got this type of dispersion figure. So this is the Kx and this is my K0. Kx is greater than K0. That means the confinement is very high. This wave vector confinement is very high compared to free space wave vector. So from this we can justify that wave is confining more on the surface interface. So these are my results. So this is my unit cell, and I have extended this periodically all over the surface, and I designed this SSPP waveguide, which is having 14 mm and 91.2 mm. And these are my field distributions here. This is electric field, this is magnetic field. As I have already stated, TM waves supported by SPPs, SSPPs or SPPs compared to TE waves. So here, if you look at this magnetic field, see you are getting half of is enclosed with the red line, and another half is enclosed with the blue line. Like that, it is distributed all over the surface. So that's why it is clear that magnetic field penetrates faster than the electric field. So here and here at this point of time, I would like to request one of my respectable DC member has asked this: what is the fabrication tolerances you have calculated? But I didn't done that, sir. Sorry, for apology from my side. I will do that, and I will report, sir, soon. And this is my simulation. This is my simulation characteristics, and these are my fabricated devices here. And one of the respectable DC member has answered, has raised one query: have you got this gain improvement? That I can answer, sir, now. So here, these are the corrugated metallic surfaces which is having 1 mm width, and this I have made it to 2 mm, and I got this type of gain improvement. So this can be achieved like this, sir, from these S parameters, successive iterations of 1 mm. 1 mm, like for example, this is 1 mm and this is 2 mm improvement. So 1 mm means for each and every successive iteration, I have raised the corrugated width to 0.1 mm each side. So like that, I got 10 readings of S parameters. So 1 mm, 1.1 mm, 1.2 mm, 1.3 mm, up to 1.9 mm and 2 mm. For 2 mm, I got this type of gain up to 7.9, and for 1 mm, I got 5 mm of gain. So how this achieved? So this has been achieved with this, sir. So with this formula, gain is equal to 10 log P naught by P in. And after calculating this, for each and every iteration, I have changed it to linear value of gain formula, 10 log gain by 10 dB. And that I got for 1 mm, I got 5.012 scale. And for 2 mm, I got 7.943 variation. And that I have plotted here. So like that, I have done this. I hope this is clear for one of the respectable DC member, Amarjit sir. And this is my second objective. This is very significant result. And this to get this result, I struggled a lot. Up to 1.5 years to 2 years, I spent time on this. So here, this is the patch fed dielectric rod antenna, which is excited with patch, microstrip patch. It is excited, and now I have removed this patch, and I have introduced this SSPP feeder element to this dielectric rod antenna. Before patch feeding, it exhibits the gain of 8.13 dBi, and after removing this patch and introducing this SSPP feeder element, it is obtaining the gain as 16.4 dBi. The gain is improved enormously. So this is my achievement. And here, if you look at the impedance matching here, before for single rod, we got minus 25 dB of gain, and for SSPP, patch feeding rod, I got minus 25 dB of impedance matching. But whenever I remove this patch and I inserted this SSPP feeder element and excited this rod antenna, then I got this value higher, and the bandwidth is also higher compared to the previous one. I got the higher bandwidth, approximately I have listed here 38.8 bandwidth I obtained here, and these are the improvements of the existed design to that of my comparisons with that of existed designs of my work. So this is my work, 7.2 gigahertz I got, and 16.4 dBi gain is improved, and here 36.3. Here the thing is that this is operating in millimeter wave band. And by using this feeding technique, I reproduced the result in terms of lower frequency range. So this is my achievement using SSPP, spook surface plasmon polarity, and I got in lower frequency range. The result has been established. And these are the reflection coefficient calculations and VSWR calculations, and it lies in 1.52. And it lies in the range of 1.5 to 1 mm, so that is 1.39. So this is the simulated VSWR. So at 7.2 gigahertz, it is slightly lying in approximately 1.39, somewhat like that, 1.2 or 1.39. So hence it is matching with simulated result also, the theoretical calculation. So everything is this. And the next, and this is the measurement setup. So I have measured this impedance matching here, and this is the first figure. After successful iterations, I got this type of image here. This is the first image I have captured here, and these are the electric field and magnetic field distributions. Sorry, this is the E plane and H plane distributions, radiation fields. I got like this. And what are the advantages? It is simplified structure, and it is having low operating frequency. By using SSPP concept, we have successfully reproduced the spook surface plasmon polarity and waves to the lower frequency range, from higher frequency millimeter wave band to lower frequency range. That is the advantage here, low operating frequency and enhanced gain. Gain has been improved, and improved impedance match and cost effectiveness. It is very low cost. We can easily fabricate this using PCB machine, and using Gerber files we can easily fabricate this. And what are the disadvantages? Feeder length. This feeder length has to be very high. This has to be reduced. That is the disadvantage here. And complex field interactions, we can't exactly differentiate which field what we can't approximately differentiate radiating or non-radiating fields here. So that is the one of the disadvantage here. And coming to the acknowledgements, I would like to express my sincere gratitude to my research supervisor and my guide, Dr. Srinivasulu Tupakula sir, because he is the one person who his knowledge is, he is having incredible knowledge on the expertise and insights into the subject, and his knowledge has been invaluable to my research, and he encouraged me, and his constant support and encouragement is pivotal in my research helping me to navigate the challenges and stay motivated. And he helped me to grow as a both researcher and as well as a professional. So I'm very grateful to Dr. Srinivasan Tupakala sir. And coming to my second
Keep it on.
so he's having incredible expertise and insights into the subject, and his knowledge is very useful to my research, and he has given me constant support and motivation so that I can easily navigate my challenges and I stay motivated. And my second one is one of my best colleague in SRM University, Mr. Imam Wali Sheikh. I really appreciate his efforts because his analysis on the topic of spook surface plasma and polariton is very helpful for my research. And his dedication, and it is clear that he put a lot of efforts and dedication and a lot of thoughts into it, and it helped and it strengthened our findings, and it helped me a lot to move my research forward. And I'm very grateful to Mr. Imam Wali Sheikh as a well-wisher and my colleague. And next one is SRM University management for giving financial support for 4 years, and my family and my well-wishers and my friends for their unwavering encouragement. With this note, I will, and these are my list of publications. So I have published 2 papers, and 1 paper is under review, and other works I'm having 4 publications and conferences and patents. And in this 2 patents comes under my topic, and rest all the other works. Thank you.
Good evening, Professor Rastogi, sir.
Yeah, good evening. Good evening.
Thanks for joining, sir.
Yeah, it's fine. So
Your comments and
yeah, Rishitesh, you said that for these terahertz, what frequency range of terahertz exactly you are targeting? So only millimeter wave you are going, or even more than that?
As of now, only millimeter wave bands, sir. 56 to 65 gigahertz. I worked on it. 56 to 65 gigahertz.
Okay, so you are not basically going towards actual terahertz, which I would say 1 terahertz to 10 terahertz or 100 terahertz.
No, sir. Actually, that type of equipments are not available till now, sir. Only 140 gigahertz is the final, one of the potential candidate for terahertz frequency, sir. 140 gigahertz is one of the potential candidate, and 330 gigahertz is another potential candidate, sir. So we are doing the research in that range only, sir, as of now.
Okay, and what is the motivation for around 40 gigahertz?
40 gigahertz.
That's what you are doing, no?
Yes, sir.
So what is the motivation for doing this?
So motivation in the sense to reduce the operating frequency to a lower frequency range, sir. Motivation in the sense to design compact integrated circuits more easily.
No, I mean to say for what applications you are targeting it, this 40 gigahertz band.
Applications in the sense, all the communication applications, sir, like military, defense, radars, 4G, 5G. It can be used in anywhere, sir.
Okay. You said that instead of dielectric wave, this MIM waveguide, you want to go for plasmonic waveguides, correct? But plasmonic waveguides have their own loss. So how do you tackle that problem?
Plasmonic waveguides.
Have their own loss.
In terms of which losses, sir? I didn't.
Propagation loss.
Propagation. Actually, group velocity gets reduces, sir. Group velocity gets reduces and propagation losses are there, but it is not that much of consideration, sir. You can't
For your
consider.
frequency.
As of now, in my research, I didn't consider much on the propagation losses. I got straight away the results, sir. I don't bother about that propagation losses. And
But have you calculated?
no, sir. Propagation losses I didn't calculate it, sir.
Okay.
Maybe I will explore that, sir.
And in one of your objectives, can I see the objectives again? The list of objectives.
Yes, sir. Yes, sir.
No, you have unshared it. It was shared earlier. Now you have unshared it.
Now it's clear, sir.
Yes. So your first objective was to design a spoof SPP waveguide and analyze its performance through modified groove width.
Yes, sir.
And second was it is to be used as feeder to feed high frequency dielectric rod antenna. Okay. Can I go to next slide? Yeah, next. Your results of this objective one. Yeah, well, hold it here for time being. So you said that this red curve, okay,
Yes,
this
sir.
is the wave vector of surface plasmon mode for this geometry, this H-shaped geometry.
No, sir. It is the wave vector of the spoof surface plasmon polariton modes.
Then it's fine. If you associate it with a geometry, then I have a problem.
No, sir. No, sir. Absolutely not.
Okay.
That's why they have mentioned there with KX, sir. KX is nothing but interface, x-axis interface, sir. The wave is propagating along the x-axis, which is meant, that is nothing but propagation vector, KX, I have mentioned there. On
okay.
that, yeah.
And the metal thickness, you are saying it is about 35 micron.
0.035. Yes, sir. 35 micron.
Okay. And what is the skin depth of your this wave, this frequency into this metal? This is copper or what?
Copper only, sir. Top and bottom surfaces are copper. Middle surface is dielectric, sir.
So what is the skin depth of 40 gigahertz into copper? Have you calculated?
No, sir, not. I directly designed this, sir. I didn't underview those minor details.
Okay, please come to the next. Yeah, here, what do you mean by gain? Because I don't know, it might be in your terminology, but to me, there is no amplifying medium, no amplification. So why you write gain here?
Gain is the sense, just it is indicating the performance of when you change the groove width from 1 mm to 2 mm, how the performance of the SSPP will look like. It is one of the parameters, sir. I have mentioned it here.
So you mean to say enhancement?
Yes, sir, exactly, sir. Enhancement.
So performance enhancement is fine, but if you write gain, technically gain is for an amplifier.
Yes, sir.
It is a misnomer.
Okay, sir. I take it, sir. Actually, that gain is calculated indirectly with this formula, sir. With this formula, sir. 10 log P naught by P in. P naught by P in I have taken from this S parameter results, sir. This magnitude results, and I have put it
No,
on.
so P naught is basically output power, no?
Sir?
P naught is output power.
Yes, sir, exactly.
No, so output power
Ah,
cannot be larger than input power.
yes, sir. Yes, sir.
Okay, so if you again go to that expression, so the value of gain will come out to be negative.
Yes, sir. Gain will be
Correct.
negative.
So with this definition, gain would be negative, and you have reported all these gain positive. How come?
Actually, here in the formula, 10 log, actually minus, sir. Numerator I will get minus, and input power also I will get minus, sir. Both will get cancel out.
No. You see, it's very simple thing. All right. If your P O over P in is less than 1, then your gain would be negative. Okay. And it has to be less than 1 because output power cannot be larger than input power. There is no process of amplification here.
No, sir. It
Correct?
is. Actually, I'm not talking about amplification here, sir. Just the performance enhancement I'm talking about here, sir. I'm
No,
not seeing any amplification factor
no,
here.
I am just trying to correlate the results that you have plotted here in this slide with the expression of gain that you have written in the slide.
Okay.
Okay, and I am not able to correlate these two things.
I have to change that, sir, to enhancement. Like that.
Enhancement and then the definition of gain that you have written, that would be the same. Yes. So please look into it. Okay. So I have a little problem here.
Okay, sir.
Correct. And let us come to your result, experimental result. Yeah, this. So what does this tell you? What you have shown here?
So I have shown here the impedance matching results, sir.
No, you
Uh,
have shown the reflection coefficient, no, S11 parameter. Okay.
On right hand side, the anechoic chamber E plane and H plane values, sir. Measured and simulated values.
No, not right hand side, left hand side.
Anechoic chamber measurements, sir. Right hand side.
No, left hand side. I'm
Left.
asking left hand side. So S11, you see in the picture, what I see here, in the previous slide, you have also plotted this. Maybe,
Yes, sir.
yeah, here, you
It's the
see.
representation of my significant results, sir.
Hmm.
Compared to that of millimeter wave frequency, my result came in terms of only 10 gigahertz, below 10 gigahertz range. I accomplished this result.
Okay.
Comparison, sir. That's it.
So here I see, several dips here. So what do they signify? Because I am getting around 7 gigahertz also, or 7.5 gigahertz, 6 gigahertz also I am getting.
But here I have taken major lower value, sir. Very lower reflection coefficient value I pointed out here, sir, as 7.3 gigahertz. So if I start simulating in that what you said in that 5.9 gigahertz dip also, I'm getting lower gain, sir. But at the I'm getting only at one point my gain is increasing to 16.4 dBi, and that is 7.2 gigahertz. Hello?
Yes, I'm just trying to look at it. So this is your S11 reflection. What about transmission?
Transmission coefficient 0, sir. Zeros.
Hmm.
I didn't mark that, sir, here. Mentioned.
Okay. Okay, this is fine. So what I'm seeing that you have dips at different frequencies.
Yes, sir.
Okay. So for which frequency you have designed and why you are getting at different frequencies and what do they signify?
At different frequencies, if I try to simulate it, I'm getting,
No, within this itself, you see, you are getting one dip at 7.5 gigahertz, another at 6 gigahertz, another at 5 gigahertz.
sir. Yes,
Okay,
sir. That range I'm getting least value, sir. Least value of gain. Those ranges I'm getting low gain, sir. But at exactly higher value, 7.2 gigahertz, higher dip, I'm getting exactly 16.4 dBi of gain. That's why I have taken that.
okay. So you mean enhancement? Enhancement is maximum there.
Yes, sir. Exactly, sir.
Mhm. Okay, I think this is fine from my side. Yeah. Okay. Okay. Thank you.
Just one question. Maybe I will have like more questions based on that. How can you decide like whatever radiation pattern you are seeing? Okay. First, whenever you are presenting graph or result, try to put as a normalized field. Okay. Whatever you are presenting. So first thing, like how will you confirm that your rod antenna is radiating your energy compared to your like field?
Here, sir.
Yes.
Rod antenna is radiating. How I?
Yeah, because I can see like if you add your feeder here element along with rod antenna, and if you see like when your radiation pattern and all, I'm not able to understand like which part of your design is radiating. Can you explain it?
Whole rod, sir, is radiating. Whole rod. Starting from L3 to L1, sir. L1, L2, L3. See, here I mentioned, sir, see, the gradually increasing, sir. The radiation is gradually increasing. Here minor, here somewhat high, here somewhat high. At last, we are getting greater radiation.
And I'm not able to understand like here you have taken like S11 parameter at like between 56 to 62 gigahertz, right? So how you mapped it from there to here?
Actually, this is without SSPP feeding. I got this patch feeding results, sir. This is patch feeding results, sir.
Okay.
And this is SSPP feeding results, sir.
Then why you are comparing at two different frequencies? It should be like same frequency range.
Yes, it should be like same frequency, but the research is that, sir, I have to reduce this to lower frequency range.
What is your response between 2 to 10 gigahertz?
2 to 10 is the low frequency range, sir.
Okay.
Response.
Go to next slide. Next. Have you measured like this pattern at different frequency also, like some other frequency? What?
Actually, I got on this, I got at 7.2 gigahertz only, sir, higher peak. So at that range only I measured, sir. We can only 2 graphs.
Can you go to like your unit element?
Where, sir?
Unit element. Okay, from here to next one, when you did like you designed everything, you did it for unit element, right? But if you go to next slide, here I can see like your unit element is not constant, it's varying. So how you did all these things?
So that is impedance matching, sir. I'm just matching this. Actually, unit cell, I got this type of bounded wave, sir. So if I use this type of corrugated surfaces, starting from 1 mm, 1.5 mm, 2 mm, 2.5 mm, then it is matching with that of light line dimensions. K naught wave vector is combining with that of K naught wave vector. So here
Which solver you have used?
CST,
Solver.
that eigenmode solver.
Here also, like when you are showing this, what is current, they have like different units and try to present it as a normalized one. Okay. Otherwise, it will be difficult to compare or understand anything. You are giving two different information. Okay, that cannot be compared.
Yes, sir.
Right? And also,
Actually,
as Arjun
magnetic
professor has
field
pointed
unit.
out this gain and all these things.
So that is
So
magnetic
try
field
to
unit.
okay.
Is ampere per meter is magnetic field unit, sir. Volt per meter is electric field unit, sir.
Whenever you are presenting, try to have like same uniformities will be maintained.
Okay, sir.
Otherwise, it will be difficult to understand. Okay.
Yeah, I have a few inputs, Mr. Vestesh. I think already the subject experts have commented on the, technicality and all is fine. But what I suggest is, for every figures, you can have some label. See, there is a confusion, right side, left side. You need to have the label, and the label should say like exactly what the picture is depicting, right? However, we do in the paper, figure 1, figure 2, and all. This is the first key thing which you need to just do. Maybe also the second is like, I couldn't even see the slide number is there, or is it hiding somewhere?
No.
So, generally, I think when we give the inputs,
I was asking you to note down the slide number. There I didn't see this.
with the slide numbers only, we give comment, go to slide number 12. In the Viva also, that's what happens. Okay, and in the initial slides, however, you have detailed, so well from the beginning onwards, well appreciated. But with that, you need to just also include the citations from where you have taken those.
References.
That was a completely missed, because the problem statement, whatever you have identified, is the important task in your PhD, right? That
I have stated only one citation.
yes,
JB
I was surprised. You have given some bold statements about somewhere before also, but that you cannot directly you cannot, right? So you should just label from the first slide onwards, from where you have taken, that has alluded to your problem statement. This is one thing. And the last one in the conclusions, whatever you have, can you please just go to your conclusion slide? And once problem statement, please. Problem statement. Okay, maybe the problem statement cannot be a problem paragraph, my dear. Okay, maybe you can little streamline that. Okay, that is one thing which I was thinking. Yeah, please.
Conclusions.
Conclusions was not there, but you okay. Then can you go to the results? I think conclusion is very, very important. Okay, that is the concluding point where what your actual research is talking about.
Summary.
Okay, summary of what exactly went, and even see the title here, it is something like outcomes. See, it is a too generalized title. Maybe you can also discuss with sir. No, you can. Objective 1 is fine, but with respect to objective 1, you must have a defined outcome there. Right? Technically defined outcome. That should reflect that under that this picture should come. Okay, and conclusion should be there, and conclusion should be something like, with quantitative metrics, you should be able to explain. You are saying the lowering the frequencies or you're hiring. No, you need to just comment. See, that's the examiner was commenting as something like, What is the motivation? Motivation is not to bring down the lower range or a higher range, whatever it is. It is all about for this application, there is a great demand for this. For that, my research is happening. You know, this should be the proper.
I kept this in the beginning. Motivation.
No, it's okay. These are all the inputs for your, you know, so that you can really do the best in the Viva voice. Okay, that's it from my side. Wish you all the best.
And one more thing, like, you have taken so much time for your introduction and all these things. Talk more about your result, your work, what you did. Okay. You can skip those kind of things.
Now the respectable DC member has asked me to do more mathematical analysis like this.
Yeah, it's for you. Okay, it's for you, but for presentation, it's too much. Okay, talk about your result. I want to see your work and all these things. Like right now, you have used just 5-6 slides, right? I want to have like at least more than 10, 12, or even 20 slides. Your measurement setups, conditions, how you did all these things. What was your like observation when you had like only broad antenna, when you connected it? Those analysis I want to see.
Elaborate more.
Okay, so don't focus on introduction and all these things. Your objectives, what you will achieve, what will be your extension of your work. Okay.
And
So those
also
things are
added to
missing.
one, you know, maintain throughout the same font size.
Yes.
Somewhere you have cut and copied also. Since the exams are not here, I am just commenting this. Somewhere you have cut and copied, some say on the left hand side as.
Without references.
No questions from the scholars at all?
Yes. Similar down.
So no, when we ask a question, is nothing wrong. It's actually we're giving some
That will
inputs to
help.
them.
That will help the scholar.
So when the external member comes in the Viva and all with more confident way, they'll be there. Yes, sir. Thank you. Wish you all the very best.
Okay. Post it is
Patient, sir.
sign on.
Sign out చేశాను సార్ sign out అయింది
ఇందులోనా అందులో సైన్ ఇన్ అయ్యారు స్క్రీన్ లో సైన్ ఇన్ అయ్యారు
సార్